Galaxies are massive self-gravitating systems of stars, either alive or dead, very cold dust, gas at various temperatures and degrees of excitation and ionization, from a few Kelvin to millions of Kelvin. A further fundamental but yet poorly understood component is dubbed dark matter, which, as far as gravity is concerned, behaves as baryons do, but does not interact with electromagnetic radiation, thus it does not shine. Galaxies are very stable systems. Looking back in time, we see that they evolve slowly, mostly because of intrinsic aging and partly because of interactions with the environment. The light of a galaxy is produced mainly by its stars. They are very numerous. A typical galaxy has 100 billion stars, or better, a mass equal to that of 100 billion suns. But they are very sparse. The distance to Alpha Centauri, the closest star to us, is 4 light years. The consequence is that the surface density of light is quite feeble. Galaxies are not visible with naked eyes. We need at least a medium telescope to observe them. The revolution in the extragalactic world started with the 100-inch Hooker telescope at Mount Wilson, California. The larger the collecting area, the better the resolution. For very distant objects, though, which look as point-like sources, we need larger and larger telescopes as the VLT. Stars are distributed in galaxies within volumes that resemble either thick spheroids or thin disks. After Edwin Hubble, we shall call these main types with the name of ellipticals and spirals. These two forms may also coexist in a single galaxy as subsystems. Ellipticals may have distinct nuclei, while spirals possess an inner bulge resembling a small elliptical, while it is not. Spheroids are typically supported by pressure, a way to say that gravity is opposed by the random motions of stars resembling a gaseous pressure. On the contrary, disks are characterized by a well-organized rotation. Roughly speaking, stars follow almost circular coplanar orbits about the center, all in the same sense as a record does in a gramophone. The difference is that the record rotates rigidly while galaxies do it differentially. This fact sheds light on the nature of the spiral pattern decorating Galaxian disks. If they were material that is integral with the disk, they could not be long-lasting, contrary to observations. Thus, a theory has been developed that traces arms as quasi-static density waves, traps for the gas and dust, and consequently regions where star formation occurs. But there, where you have young stars, you find emission nebulae. So, spiral arms appear as neon signs at the top, at the roof of underluminous solid buildings of stars. They shine a lot, but contribute very little to the mass. Gas is not located in spiral arms only. Together with dust, it may reside in the galaxy nuclei to be eventually eaten by the massive black hole sitting at the center of galaxies. It can mark disks, or it may extend beyond the luminous outskirts of a galaxy disk to form a sort of neutral hydrogen cloud at the outskirts of the galaxy itself, which shines in a spectral line in the radio domain at 21 centimeters. It can also extend in form of ionized plasma, usually into two opposite lobes, shining radio waves, or in hot halos shining X-rays. While stars of bulges and of stellar halos are usually old and even extremely old, those in the flat disks can be also very young. This generates remarkable differences in the colors of the stellar populations of these subsystems. The reason is the following. Take a coeval population of stars of various masses. At an early stage, the brightest individuals of this population are the most massive stars, which are very blue. Billions of years later, these stars have disappeared, leaving as brightest individuals the intermediate mass stars, which have evolved into giant red stars. Galaxies may have active nuclei and peculiar nuclear structures, including counter-rotating cores. Galaxies are sparse within the cosmic horizon, 500 billion nebulae within a sphere of 50 billion light-year radius. They group in clusters or live in relative isolation. We call this ambient the field. There is an apparent correlation between morphology and clustering level, elliptical like the crowd, spirals don't. Crowded sites induce interactions. That is, galaxies evolve due to plane aging, due to the feedback given by, for instance, the explosion of supernovae, which quench star formation by sweeping out the interstellar material, and by interactions with the environment. This is a rather complicated picture to reconstruct. To get started, we shall ignore all these complications and try to depict first the structure of galaxies as they look like, forgetting time evolution.